Hello, this is Professor Kuehn. Welcome back to my lectures on astronomy, where we are looking at Edwin Hubble's book, The Realm of the Nebula. In my last lecture, I gave a brief introduction to the science of spectroscopy. What is spectroscopy? It's a technique for breaking light into its component colors. This technique not only was pivotal in developing the modern theory of matter, but it also played a key role in giving modern cosmologists an understanding of the shape and distribution and motion of the nebula filling the universe. We're on about page 327 in a student's guide to the great physics texts, and we are going to start talking about how the technique of spectroscopy specifically was used by astronomers to understand the motion of the universe. If you look at the second full paragraph on page 327, Hubble says, finally, there are absorption spectra. When an incandescent solid, giving of course a continuous spectrum, is surrounded by a cooler gas, for instance, a star surrounded by an atmosphere, the gas absorbs just those colors which it would radiate if itself was incandescent. This absorption produces dark spaces or lines in the otherwise continuous spectrum of the background. The patterns of these dark lines identify the gases in the atmospheres of the stars. So now what Hubble's doing is he is talking about applying absorption spectroscopy to understanding the composition of the galaxies, or more specifically, the atmosphere surrounding the individual galaxies. So you might remember, if a star or other incandescent solid object emits white light, and that white light passes through a cool gas, that gas will absorb certain colors from that light. And so if you're looking at that nebula through a telescope using a spectrograph, those particular colors will be missing. They will show up as absorption lines in the spectrum that you achieve. The study, he says, of absorption spectra is the dominating feature of modern astronomy. And then he goes on to talk about some of the specific information one can get from absorption spectra. Perhaps the most important thing, as I mentioned, is the absorption spectra provide information about the speed of the nebula. How in the world do absorption spectra tell you something about velocity? Well, in order to understand that, one must understand the concept of the Doppler shift. So let me do a brief digression and talk about Doppler shifts. What is a Doppler shift? Well, you're probably familiar with it already. So if you've ever stood near train tracks as a train is approaching and a whistle goes off on the train, the pitch of the whistle changes when the train is approaching you compared to when it's passing you, compared to when it has already passed you and is moving away from you. Specifically, you probably notice as the train is coming toward you, the whistle sounds a bit higher in pitch. And then when it passes you and it's moving away from you, the pitch drops a little bit. It sounds like a lower pitch. Why is this? Well, sound is a wave. And if the source of the waves, of those sound waves, is moving toward you, the wavelength, or the distance between the compressions of the air, is actually scrunched up a little bit. The wavelength is decreased. A decreased wavelength implies a higher frequency of light, or a higher pitch. On the other hand, when the train is moving away from you, the source of the sound is moving away from you, the sound waves are more spread out. The wavelength is longer, and the pitch is lower. This is called a Doppler shift, and in fact, by measuring the change in pitch from when it's going toward you to when it's going away from you, one can determine the velocity of the train. There's a formula relating the speed of the source of sound to the shift in frequency that was very well known at this time. Now, what does this have to do with looking at emission spectra, or absorption spectra rather, of galaxies and determine their velocities? Well, you might anticipate where this is going. If a particular nebula is sitting still, then the absorption lines, which are related to the frequency and the wavelength of the light that is coming to us, are going to have a particular well-known wavelength. But if that galaxy is moving toward us, then that wavelength is going to be shortened, kind of like sound waves are shortened when a train is moving toward you. The light waves, the wavelengths are shortened, and hence the frequency of the light is higher, and higher frequency light is more toward the blue end of the visible spectrum. On the other hand, if the galaxy is moving away from us, then the particular color of light that is absorbed by the gas surrounding the nebula, that particular color appears at a longer wavelength. That's because the stars are moving away from us, and hence the wavelength is more spread out. There's a lower frequency, and this corresponds to a redder color. So by looking at the blue shift, so to speak, or the red shift of the absorption lines, one can obtain information about the velocity of the nebula compared to us. This is precisely what he is talking about on page 328. So he mentions here the specific absorption lines that are apparent not only in our sun, but also in galaxies. So let's pick up on page 328, the first full paragraph. He says, yellow stars like the sun, our sun, show the absorption of hydrogen and of iron vapor in their atmospheres, and near the violet end, a pair of strong dark lines due to calcium absorption. These latter, the so-called H and K lines of calcium, so the calcium vapor absorbs those particular frequencies or those particular wavelengths, those are called the H and K lines of calcium. These are the most conspicuous feature, the most obvious feature of the spectra, and are unmistakable wherever they are found. On the same scale, the spectra of nebulae resemble those of yellow stars. Remember, nebulae are composed of stars. So the spectrum of the nebula resemble those of yellow stars, and the H and K lines are readily recognized, and certain hydrogen and iron lines are recognized as well. So by looking at the spectrum of these nebula, they are basically a continuous spectrum, all the different colors, but with particular lines, a pattern of absorption lines that are easily recognizable, these H and K lines. And one can look and see the position of these H and K lines and measure the wavelength or the frequency of the light that's producing these H and K lines. And here is the important point in the next paragraph. He says, the spectra of nebulae, however, exhibit a peculiar characteristic in that the details, the dark lines, the absorption lines, are not in their usual positions. That means they aren't of the wavelength or the frequency that one would expect if those were stationary, like you typically measure those lines in a research laboratory here on Earth. They are not in the regular positions. The lines are all displaced toward the red end of the spectrum, and the displacements increase with the faintness of the nebulae observed. The observations are summed up in the statement, the fainter the nebula, the larger the red shift. So if we look at figure 26.6, to which he refers now, in this diagram, we show the absorption spectrum of not only the sun, but several different galaxies that are at different known distances from us. So the top diagram, we show the absorption spectrum of the sun. Just worry about this white band right in the middle here, and you'll notice he has an arrow pointing to two dark lines. Those are the H and K lines, the absorption lines that are in their regular position because they're measured in the sun, which is pretty close to being stationary compared to us. I know it's moving a little bit compared to us, but not toward or away from us, so you wouldn't expect to see any kind of Doppler shift. But now notice a particular galaxy, NGC 385, which is at 23 million light years away from us. This, of course, is measured by the faintness of the galaxy, as mentioned earlier in this Hubble reading. Now notice the same lines, the H and K lines, but they're at a slightly different position compared to that of the sun. They are shifted a bit more toward the red end of the spectrum. That is, their wavelengths or their colors are a bit reddish. Now look at the next galaxy, which is NGC 4884, which is 45 million light years distant. There's a photograph of it through a telescope. And I think this telescope was taken at the Mount Wilson Observatory. That's what it says in the caption. Mount Wilson Observatory is in California. Notice once again the conspicuous H and K lines, and those are shifted even a little bit more toward the red end of the spectrum. Of course, this is a black and white photo, so you can't see the colors. You'll have to trust that. Then there's the nebula in Ursa Major cluster, which is 72 million light years distant. Once again, the H and K lines are visible here. And the nebula in the Leo cluster, which is 105 million light years distant, and you see they're shifted even more to the right. So you see this distinct red shifting of these lines. And what does he say? He says, now the apparent faintness of nebula is confidently interpreted in terms of distance. This is what I just mentioned. The fainter ones are the more distant ones. Hence, we can restate the observational results in this form. Redshifts increase with distance. Precise investigations indicate that the relation is linear. Redshifts are equal to distances times a certain constant. So if we look at figure 26.7, this is Hubble's famous plot of the redshift compared to the distance. And notice that on the vertical axis, he's putting the velocity. What he's done is he said, well, redshifts, as I mentioned a few minutes ago, can be translated into velocities if we interpret them as a Doppler shift. The more redshifted ones are moving at a higher velocity away from us. And there's a well-known relationship between the Doppler shift and the velocity. So you can plot the velocity of these various galaxies as a function of the distance that they are located from us. And you find out that the ones that are more distant from us are certainly moving, according to this interpretation, at a higher velocity. If you look at the slope of this line, it's about the velocity increases by 5,000 kilometers per second for every 10 million parsecs that a star is more distant, or a nebula is more distant, or about 500 kilometers per second per megaparsec. That is known as Hubble's constant, by the way, 500 kilometers per second per megaparsec. It's the slope of that line. By the way, more contemporary measurements of this do not agree with Hubble. They do show a linear relationship, which I'll show here, but the slope is very different than the one that Hubble originally measured. The contemporary measurement is something like 70 kilometers per second per megaparsec. So notice, this implies that the galaxies that are more distant are moving faster away from us. And this is precisely the piece of information that led to the idea of the expansion of the universe. Now, it's important to recognize that there are a few different interpretations of this. And so in my next lecture, I want to talk about how one might interpret this famous redshift data and the Hubble relationship that was discussed here.